Now in this example also we have a region of space which has more or less uniform magnetic field. This time the magnetic field is into the board, and the wire has two straight segments and then a segment that is a semicircle with a radius r. So we are required to calculate the total force acting on this wire. Now again note that if you look at this segment of the wire, the current, let's say it's moving in this direction, the current goes up and then down. In this segment, the current is moving upward, the magnetic field is into the screen, so I cross B is towards our left. So this is the direction of the force acting on this segment. And on this segment, the current is moving down, our forefingers should be down. Palm is in the direction of the magnetic field into the screen. My thumb is now the direction of the force. So the force acting on this segment is in the opposite direction. Furthermore, we know that the magnitude of the force is given by ILB times sine theta. In both of these cases, here and here, the I is either going up or going down. B is always into the board. So this theta is always 90 degrees, sine theta is 1. For both of these segments, I is the same, L is the same, and B is the same because B is uniform in this rectangular region. So that tells us that these two forces, they are pointing in opposite direction but have the same magnitude. When we sum them up, those two forces just give us 0. The only other contribution that we need to calculate is the force acting on this segment. Now we see that I is, okay, so along this segment, now the direction of I, L cross B, the direction of L is constantly changing. So there are a couple of approaches we can do in this case. We can say that since L is constantly changing, we will be dividing this segment into very small parts. We can pick one of those segments. Let's say we took this segment over here. Then dl is pointing in that direction. That is the force acting on that segment will be I times dl cross B. dl is pointing in that direction. B is pointing into the screen. So dl cross B is, this is the direction of df. So to calculate the total force, in that case we need to sum of all these df's around this arc, which is given by I dl cross B, which is equal to, well, I is a constant, it is the same for all segments, we can just take it out. B is also a constant over the segment, B is the same everywhere, so I can also take it out. But note that as we have the property of the cross product is that if you change their order, there is a minus sign. So I don't want to change the order. I will take B out of the summation sign, but it is on the right of the summation sign. And now we have this sum of dl. Now what is this sum of dl? Well, here we have all these very small segments, one dl, the other dl, dl's corresponding to each one of those vectors, all of those segments. So we are summing all these vectors. But those vectors are already one after the other one. So the sum of such vectors, the definition of the vector sum is that the result, okay, so we are just summing all these sums. The result is a vector that points from the start of the first one and ends at the tip of the last one. So this is the sum of dl in this case. Now, let me call that large L. So the force is I times that large L cross B. Now, L cross B, L is pointing in that direction. B is into the screen, so L, I point my four fingers in the direction of L, such that my palm is somewhat pointing in the direction of B, then my thumb points in the direction of L cross B. So this is the direction of the force. And the magnitude of that force is I. Well, the magnitude of L is the diameter of that semicircle, and hence the diameter is 2r because the radius is given as r. And the magnitude of B is B0. And this is the magnitude of the force.